I'm just giving you the overview of combinational circuits. The reason for that is because in the next unit we are going to start with sequential circuits. So before you start with sequential circuits, you must be having some idea about how your gates are being made of transistors and all. And there are several advantages of CMOS that will come into the picture. So, what are the contents of this module? The first thing is we are having some overview of CMOS technology. Second point is various implementation of basic gates. And after that, I will try to implement a simple expression with the help of your CMOS. Then last, what are the other alternatives beyond your CMOS technology or architecture? So these are the 4 different points which we are going to cover in this module. So first advantage of CMOS technology is it is having low power dissipation. And this I have already discussed when we are covering the topic your different inverters using different loads. So the advantage is low power dissipation because static power dissipation is very low. So that is the reason your power dissipation is on the lower side. The dissipation happens only when there is some change in level and some dynamic thing is there. Otherwise, there is no dissipation. Now, next thing that is of importance is easy to fabricate. Because most of the fabrication labs these days are working with CMOS technology. So there is a well-known procedure by which things are being fabricated. So that's why CMOS is quite easy to fabricate using various procedures, twin tub or twin well, N well, P well. So fabrication is quite easy. So that's the other reason CMOS technology is being preferred. Static power dissipation is zero, that I have already discussed. Then other thing about your CMOS technology is to implement any logic, you need 2n number of gates. Suppose you want to make an inverter. So inverter is having one input. So how many gates are required? 2n. Two gates are required. Two transistors are required. Similarly, if you are having two input AND gate or NAND gate, so how many transistors are required? 2 into 2. So 4 transistors are required for a NAND gate. So this is just the overview of CMOS technology. Now, what is the other advantage? The other advantage is when you actually scale the technology from one level to another level, then same architecture can be implemented for scale technology. So thus saving the time. It does not mean that every time you are scaling the technology you have to change the designs and all. Everything remains same. Only certain things related to them will be changed, but most of the things are same. So that's the advantage of CMOS technology. So what is a combinational circuit basically is? So all of you are aware of that when a group of circuits are combined together, gates are combined together to give a particular output, that is called combinational circuit. So we are giving input and correspondingly we are getting output. So your output is determined only by the current inputs. So whatever your inputs, your output will be there. So there is no storage, there is no other thing for which your device can be utilized. So next thing is the basic architecture of your system. So here you can find out that whenever we talk about your CMOS, the upper network is called pull-up network and lower network is called pull-down network. So whatever logic is to be implemented in a combinational sequence, both of them need to be in this particular fashion. That means equal number of transistors for input at pull-up network, equal number of transistors for input at pull-down network. So basically, pull-up and your pull-down are dual of each other. So, and your output is function of your inputs, which are there. So, why it is called pull-up? Because when this particular network is on, your VDD is actually charging up the load capacitance. And this is called pull down. Your this particular voltage, whatever is being stored in the previous cycle, will be discharged. So this network is responsible for charging up, and this network is responsible for charging down. So that is why this is called pull up, this is called pull down network. So next we move towards how we are actually implementing the things. So suppose y is equal to x, and now we are using NMOS as switches. So there are two kinds of connections, serial and parallel connections. Both of them will be discussed here. So transistors can be thought of a switch by its gate signal, and NMOS switch closes when switch control input is high. So when A and B both are high, then Y is equal to X. Once again I repeat, when A and B both are high, your X is equal to Y. So what does it mean? It means Y is equal to X if A and B is equal to AB is equal to 1. If any of these switches is off, Y is not going to equal to X. And if we speak in terms of equations or currents, if A is on, whatever current is there will be transferred at this particular point. And if V is on, then this will be transferred to the output. If any of these two is off, suppose A is off, this will not be transferred to here, and you are not going to get anything at the output. So that is a good thing. So whenever you want to have any sort of AND operation or multiplication operation, your NMOS need to be in series. Next is when your A and B are parallel to each other. So NMOS 1 and NMOS 2 are parallel to each other. Now X is equal to Y, sorry, Y means your output, X is equal to your input. So Y is equal to X only when any of these two are high. So when A is 1, your device is getting this particular path. If B is equal to 1, this path, and both of them are on, still you are getting the current. So your output is 0 if and only if when your both the gates are off. Both the gates are off, and or we can say your A is equal to B is equal to 0. So this can be written as like this: if A or B, or A or B. So this is your OR operation. This is your AND operation. Now the one problem with NMOS is it passes a strong 0, what a weak 1. So in the coming slides, I will discuss this particular point. What do you mean by strong 0 and what do you mean by weak 1? Now similarly, we talk about PMOS transistors. So your PMOS transistors are having serial and your parallel connection. So PMOS switch closes when switch control input is low. So what does it means? It means when A is 0, B is 0, then whatever we are having at X, that will be reflected at Y. So that means to have this series connection working, both of them should be 0. And if both of any of these two is high, your input will not be reflected at the output. So it can be written as Y is equal to X if A bar and B bar is there, or we can say it can be written as A plus B bar. You know, this is a De Morgan's theorem. So this is equal to, if this thing exists, then only y is equal to x. Now about parallel connection. So if any of these two is low, you will get y is equal to x, and it can be written as your A bar plus B bar. So this is your AND operation, this is your OR operation. Okay. The problem with PMOS transistor is it passes strong 1 but a weak 0. So we will discuss this in the coming slides. So now what is we are talking about is being discussed here. That means PMOS is good for 1, bad for 0. NMOS is good for 0, bad for 1. So this will be discussed one by one. So here you can see this is your pull-up network. So pull-up network means your PMOS. So when you have a look at this, what is the observation? That when your input is grounded, then your output at this particular load capacitance will move from 0 to VDD. Will move from 0 to VDD. That means you are getting the output to the full swing like this. So what is the output in case of CMOS inverter? Your output is always equal to VUH, and VUH is equal to VDD. Why it is so? Because this particular transistor is not getting anything dissipated in between. Now coming towards your, so this is good for 1 because you're getting very high output full swing, so your output is 1, good for 1. Now bad for 0. Why it is bad for 0? So here you can see this is your pull down network. So when your VDD is high, your this particular capacitance will grow from VDD to 0. But on the other side, what is the problem? That in your pull down network, some of the voltage is being consumed, VDD minus VTN. You are not getting the full swing when you are passing any voltage or current, any current through this. So some of the voltage is being consumed. Here you can supply some voltage. Suppose you are supplying some 2 volts here, 1 volt or something. Then some of that is being consumed in threshold voltage. So that means you are not getting a very good logic equal to 1. So that means your NMOS is actually giving you bad 1. But on the other hand, NMOS is discharging 0 completely. So this is giving you good 0. On the contrary, when you look at the pull up network, your PMOS is not discharging 0 completely, but threshold voltage of PMOS is being reflected at the output equal to VTP. That means your output is not completely 0, but some voltage is there. So that is called bad 0. So once again I repeat, this is the question some of you may be asking in the near future, that why PMOS are being used for pull-up networks and NMOS being used as pull-down networks. So this is the answer to that question. So here we are using PMOS as pull-up network. Okay. Now it is being used as pull-up network. What you are getting? You are getting the full swing. You are getting the full swing. Now here your NMOS is being used as pull-down network. So you are getting VDD to 0. That means here your capacitor is fully charged up to VDD. Here your capacitor is discharged from VDD to 0. That means it is going very good for 1. It is going very good for 0. Now the opposite case. In this case, we are using NMOS as pull-up network. So now when we are using NMOS as pull-up network, your output is not VDD, but it is VDD minus VTN. So that means some of the voltage from the VDD is being consumed in neutralizing threshold voltage. So that means it is giving you bad one. Now we are focusing on this. Here we are using PMOS as pull down network. So when you are actually pulling down this to zero, your output is not zero at CL, but it is a threshold less equivalent to threshold voltage of PMOS. So that means it is bad zero. So I hope here you are getting the very good idea how your PMOS is acting as good one and bad zero, and how your NMOS is getting at good zero and bad one, and why your PMOS is being used as pull-up network and your NMOS is being used as pull-down network. So this is the basic thing. So whenever you are actually implementing any logic using CMOS, your PMOS is going to be used as pull-up network and your NMOS is going to be used as pull-down network. Now coming to the next slide. So here, uh, the important thing that your pull-up network is dual of PDN. So suppose your pull-up network is giving you this A plus B whole bar. So using De Morgan's theorem, it is being reduced to A bar dot B bar. And if your pull-up network is AB bar, your pull-down network is going to be A bar plus BR. So that's very important. So if you are having AND gate, so it can be implemented using NAND gate and inverter followed by that. So now we are coming towards how we are going to actually implementing these gates. So the first example which I am going to discuss with you is NAND gate. So NAND gate means your output is this. So what is the truth table for NAND gate? That your output is always high, but only in the one case when both the inputs are high, then only your output is going to low. This is the function for your two input NAND gate. So here, what is the logic expression for that? So your logic expression for this is A bar plus A bar B bar. So the first thing we are going to do is pull up network. Pull up network. So here you can do it in two different styles. The first style is directly from the truth table. So from here, what is your idea you're getting for a full case of your pull up network? That if any of the inputs is zero, then your device is on and your output is high. And when both are high, both the devices are off and your output is zero. That means there is no way of movement of current from this particular portion to this particular portion. So this clearly gives us that they are parallel to each other. Now coming towards NMOS, pull down network. So here you can see that if any of these two is off, your output is high. The only case when your output is going to low, that means your capacitance is going to be discharged, is when both your inputs are actually high. When your both are inputs are high, that means if this is high, then only your output will be discharged. So this gives you a very good idea. That means pull down means your capacitance is actually going to discharge, so conduction to ground, and pull up network means a connection between or conduction to VDD. So this is example of NAND gate. Now if you want this NAND gate to be used as AND gate, the only thing you have to do is you have to use a inverter here. So this is a inverter. So here you are getting your output. So inverter will remove this and you are getting a voltage A dot B. So this is about your NAND gate. Now, next is your CMOS NOR gate. So NOR gate means your output is going to be A plus B complement. A plus B complement. So here you can see that if we look at this, solving this, you will get multiplication of A dot B bar. So it clearly shows that multiplication is there. So to get a high output, what you have to do is both of these should be on. So they are in series, and similarly, to get a high output, both of them should be off. So PMOS is off only when your inputs are 0 and your NMOS is 1, high, off when your inputs are 0. So your NMOS is on, and see, this is either of these two is one, NMOS is on, and this will be getting you the things being discharged. So that means to have your output being sustained at 1, what you are supposed to do is your input should be 0. Now this is the case for your NOR gate. If you want to convert it to OR gate, the only thing you have to do is an inverter need to be added here like this. So this becomes your A plus B like this. Okay. So now I will tell you how a complex CMOS expression can be implemented with the help of CMOS, whatever we have learned in the previous slides can be implemented. So suppose you are given a expression Z is equal to A bracket D plus B plus B plus C whole bar. So what you are actually getting here, so this is your simple pull down network. So first we have to draw a pull down network, then your pull up network. So the first thing we have to do is we assume that instead of your full PMOS, we are actually having a single PMOS, and that is always grounded. That is always grounded. That means that is on. So we try to implement a pull down network. So pull down network means here you can see A multiplied by D plus E. So multiplication means you are having series, which we have seen in the beginning slides, and addition means, yeah, or operation means parallel in case of NMOS. In case of PMOS, they are inverse. So now this is this, so that means this arm is parallel to this arm because OR operation is there. Now BC is again multiplication, so they need to be in series. So this is just fundamental. Once again I am repeating, AND operation means series, OR operation means parallel in case of NMOS. So here you can see this is one operation, this is one AND operation, this is another AND operation, this is one OR operation, this is another OR operation. So we are fragmenting into this. So this is A, this is D, E, and B, C, like this. So this is first branch, this is second branch. Now some of you may ask, sir, why D and E is not on the top and A is in the bottom? The reason for that is capacitances, because these two are also having capacitances, so they will also take some time to discharge. So thus unintentionally delaying, increasing the delays. So to avoid delay, the operation with the least activity will be put on the top, while operation with the most activity will be on the bottom, so that we are avoiding the overall delay in between, because some charge is being required to these parasitic capacitance of these transistors also. So that is the reason the maximum operations are at the bottom, least operations will be at the top. Now, this is how we have actually designed your pull down network. Now, the next thing we will be discussing is pull up network. So, the entire thing is going to be exact replica. So, this is your pull down network. Okay, A, B, C, like this. So, we are actually changing the things, and your entire thing is being reduced to this here. So, this is, I think this is for the different structure. So, but you can see here what is the structure. So, this is being a exercise to you, live exercise. So, what is this? This is your D and plus A dot B plus C. So, in case of your pull up network, your series become parallel and parallel becomes series. So this is parallel to this. So now they become series. Again, the same thing is there. That means the node should be at the closest of load capacitance. So here you can see we are putting this near to the ground. Here we are putting this to the VDD. So that least amount of activity is there. So these two are in series. So now these two are become parallel. A and this are become parallel, and here they are in parallel. They are getting into series. So you just do practice for 2-3 equations. You get a very good idea that how you can convert a complex expression into a equivalent transistor equivalent. So from here you can easily see that here you are having 4 inputs. So how many transistors are required? 8 number of transistors are required. So that means we are actually okay, this is the one which we are talking about. So this is the expression actually here. So now they are in series, so they becomes parallel. So they are in parallel, they become series. So the thumb rule remains same, that most activity in case of PMOS should be near the VDD, in case of NMOS should be near the ground, and rest other things remains same. So they have done using graph concept. So right now, because of scarcity of time, I am not going to discuss this, but you should know how you are actually going to convert a complex expression into your equivalent transistors. So you can use either of these techniques. The one which I have taught you is a simpler thing, and you can utilize it to implement a simple logic expression into a equivalent number of transistors. Now, this particular approach which we have used is having 2n number of transistors to implement any logic. But researchers are not happy with that, because they think that why to use this particular technique, because the only purpose of this logic is to just pull up. Yeah, and this is the major criteria which actually decides whether to keep this charge or not. So if somehow we can minimize this, then our thing will be quite easier, because here it looks quite simple that you are having 10 transistors, 5 for pull up and 5 for pull down. But as things becomes more complex, number of transistors will be more and more. So if you are having a million and million of modules, you are actually adding billions and billions of transistors on your IC. So that means in that case, it need to be minimized. So instead of having 5 transistors, can we minimize it to 2 or 1, maybe like that? So for that, we have different approaches. We will not be discussing in this particular course, but if you're interested, we can discuss in the later portion. So this is pseudo NMOS technique, domino logic, pass transistor logic, transmission logic, bootstrap logic, and zipper logic. So these are the certain techniques by which you can reduce the number of transistors, although they are having some there of the advantages or disadvantages, which can be dependent upon the type of application for which you are actually designing your devices. So thank you very much for this particular class. And if you have any doubt, you can ask me. So over to you people now.